In this Regents chemistry video, we're going to talk about polarity of both bonds and molecules. So the first thing we need to think about in terms of polarity is what is electronegativity. So remember, electronegativity is the attraction of electrons. So basically, we're saying how much does an element want electrons near it. If we have, remember the octet rule, if we have an element that's really close to having an octet, like fluorine, and it has one electron to gain, it's going to really want to gain that electron to fill its octet. Whereas if we have an element like sodium, which only has one electron, it wants to lose an electron really badly to get that octet. So it's going to have a low electronegativity. So things that want electrons near them are going to have a high electronegativity, and things that want electrons away from them are going to have a low electronegativity. So remember, fluorine is the most electronegative. It has an electronegativity of 4.0. So the trend in electronegativity on the periodic table, as you will remember, is that it increases up and to the right on the table. And remember, we got fluorine up here on the top right, and that's the most electronegative, so that can help you remember the trend is to the right and up for the increases in electronegativity. So this is telling us basically how much an electron wants, or an element wants electrons near it. So if we think about bonds, remember we talked about covalent and ionic bonding. So how do we decide if a bond is polar or nonpolar? Well, if we look at a bond between carbon and oxygen, we know that we have two electrons shared in here if it's a single bond. So we want to see, how are these electrons going to be shared? Are they going to be shared evenly or unevenly? So if we look at the electronegativity values, remember table S is where we can find these electronegativity values, but if we look at the electronegativity values for carbon and oxygen, the carbon value is 2.6 and the oxygen value is 3.4. So oxygen is more electronegative than carbon. That means it wants these two electrons that they're sharing, it wants them more. So the real bond between carbon and oxygen would probably look a little more like this, with the electrons kind of closer to the oxygen side than the carbon side. So because these electrons are negative, what this is going to create is a negative end of this bond. Because the electrons are being pulled more towards this side of the bond, this is going to make a negative end, and then this side is going to be more like the positive end because we've lost electrons here. The negative charge has gone away. This is going to form a more positive end here and a negative end here of this bond. So this is a negative pole and a positive pole, making this bond polar. So that's how we end up with a polar bond, is if we have uneven sharing between the molecules. So the carbon and the oxygen are sharing unevenly here. The oxygen is pulling the electrons more. That's going to make this bond polar. Whereas if we look at two fluorine molecules bonded together, or fluorine atoms, bonded together, we have two electrons in the middle here. The electronegativity for fluorine we said is 4.0, and this is just another fluorine, it's going to be 4.0. So these electrons are being pulled evenly by both of these fluorines, so they're going to be shared evenly in the middle between the two of these. So this is going to be even sharing, which makes the bond nonpolar. So basically, if you have two of the same element bonded together, that's going to make it nonpolar because they're going to have the same electronegativity values. They're going to share the electrons evenly. If you have two different elements, that's going to make it nonpolar because they're going to have different electronegativity values and therefore share the electrons unevenly. The electrons are going to be pulled more towards one side than the other, and it's going to make a negative and a positive end of that bond. So if we look at a couple more examples here, in H2O, we have O with two H's. So if we look at just one of these bonds here between the H and the O, we have hydrogen, which has an electronegativity of 2.2, and then oxygen has an electronegativity of 3.4, and again, these just come straight off of table S. The difference here in electronegativity is 1.2. The oxygen has a bigger electronegativity. The electrons in this bond are going to be pulled closer to the oxygen than they are to the hydrogen. That's going to make one end of this bond negative up here by the oxygen, and then another end of this bond positive down here by the hydrogen. Because we took the electrons away from here, we removed negative charge. That's going to make a positive end, and then a negative end where we put that extra negative charge. So this is going to be polar because we have an uneven sharing of the electrons. If we look at nitrogen though, nitrogen bonded to another nitrogen, there would actually be a triple bond here, but that's not all that relevant in terms of the polarity. These electrons in the middle are going to be shared evenly. Because we have nitrogen and another nitrogen that have the same electronegativity value, these electrons are going to be shared evenly. Even sharing makes a nonpolar bond. Nonpolar, you get the point there. So basically, if we have two of the same element, that's going to make a nonpolar bond because the same element is going to have the same electronegativity. But if we have two different elements, that's going to make a polar bond because we have uneven sharing. The electrons are going to be more towards one side of the bond, and that's going to give us a negative end and a positive end of that bond. So to sum up polarity, if you have polarity of bonds, if you have two of the same element, it's going to be nonpolar. If you have two different elements, that will make it polar. So how do we decide which bond is more polar if we compare two bonds? Well, basically, the bigger the difference in electronegativity, the more polar the bond's going to be. Because if we have a bigger difference, let's say we bond fluorine to hydrogen. Fluorine is really, really electronegative, so these electrons are going to be pulled very much towards the fluorine. Whereas if we have, let's say, oxygen and hydrogen, oxygen is really electronegative as well, but not as much as fluorine. So the electrons are going to be pulled more towards oxygen, but not so far as they are with the fluorine. So basically, the bigger the electronegativity difference, the more polar the bond is. So if we have two bonds, we can see, well, what's the electronegativity difference, and then whichever has the greater electronegativity difference is going to tell us which is more polar. So carbon, we said, has 2.6 and oxygen has 3.4, so the difference here is 0.8. Carbon, again, 2.6 and fluorine 4.0, so the difference here is 1.4. So carbon bonded to fluorine would be a more polar bond because this difference in electronegativity is greater than the difference for carbon and oxygen. If we look at the next one, we have aluminum, which has an electronegativity of 1.6, and then chlorine has an electronegativity of 3.2. So the difference here is 1.6. The bromine, we don't even have to look at this because they're two of the same element. The difference here is going to be 0. So this is actually non-polar because we have two of the same element bonded together. This is going to be non-polar, so this being at all polar is obviously going to be more polar. If we look next at sulfur and chlorine, sulfur has an electronegativity of 2.6 and chlorine again 3.2, so the difference here is 0.6. Silicon has an electronegativity of 1.9 and hydrogen has 2.2, so the difference here is 0.3. So the more polar bond is going to be the one with the higher electronegativity difference, which is 0.6. So again, if we are trying to compare the polarity of two different bonds, the more polar bond is going to be the one with the bigger difference in electronegativity. So this last one, if we look at hydrogen, which has an electronegativity of 2.2, and selenium, which has an electronegativity of 2.5, and then hydrogen, again 2.2, and tellurium, which has an electronegativity of 2.1. The difference here, 0.1, the difference here, 0.3, so the bigger difference here is between hydrogen and selenium, so this is going to be the more polar molecule. So to figure out the more polar molecule, again, we just see which has the bigger electronegativity difference. Alright, so if we look at another example here, we're going to move on to the polarity of molecules. So far what we've been talking about is the polarity of bonds. So if we have one element, say carbon, bonded to another element, oxygen, we're looking at just this bond in here. Is it polar or nonpolar? Do we have an even or uneven distribution? But what we can also look at is the polarity of molecules as a whole. So if we have, let's say, a water molecule, is that polar or nonpolar? So the key with the polarity of molecules is to look at the symmetry of the molecule. So if the molecule is symmetrical all the way around, that means it's all even all the way around, there's no uneven distribution of elements or charge, that makes it nonpolar. Alright, so symmetrical is nonpolar. If it's asymmetrical, meaning not symmetrical, If it's uneven in any way, that makes it polar. So asymmetrical is polar. So it's if you want a mnemonic here to kind of remember the difference between polar and nonpolar, you could think of SNAP. So symmetrical is nonpolar and asymmetrical is polar. So that forms SNAP, and that can possibly help you remember the polarity of molecules. So again, with a nonpolar molecule, we have a symmetric distribution of charge. It's an even distribution. With a polar molecule, though, we have an uneven distribution of charge. So this could mean we have different elements that have different electronegativities. It could also mean that we have perhaps lone pairs, which would obviously be differently charged than elements that are around a central atom. So what it really comes down to is if it's uneven, asymmetrical, it's polar. If it's even or symmetrical, it's nonpolar. So again, just think SNAP. Symmetrical, nonpolar, asymmetrical, polar. So if we take a look at these two molecules that we have here, we have the one on the left is the same shape as the one on the right. They both form this trigonal planar shape. You don't need to know all of these shapes right now, but this is the same shape. They both form this triangle, right? But the difference is here we have all oxygen molecules all the way around. These are all the same element. 1, 2, 3 of the same element around this sulfur. So this is an even distribution of charge. This is symmetrical. So if a molecule is symmetrical, that makes it nonpolar. So this molecule on the left here is nonpolar. If the molecule is asymmetrical in any way, that makes it polar. So if we look at this one, we could draw one line of symmetry down the middle here, and we could kind of fold it up and the chlorines would match up with each other. But what if we try and draw a line of symmetry down this axis like this? Then we're trying to match up this chlorine and this oxygen, which are not the same element. So this is an uneven distribution of charge, which makes it asymmetrical, which then makes it polar. So even though these two elements are the same shape, they are different in terms of polarity. So this molecule on the right is polar because it's not evenly distributed all the way around. These are two different elements here, the chlorine and the oxygen, so that asymmetrical distribution makes it polar. This, on the other hand, we have all the same element all the way around. This is totally even. That makes it a nonpolar molecule. So water is a polar molecule, and let's look at why that is. This is a very important thing to know. If we look at the water molecule, we have oxygen with 2 hydrogens, and then we have a couple of lone pairs. On the top here, we've gone over these Lewis structures. This is the Lewis structure that you should come up with for water. If you need to, pause the video, draw this yourself, and make sure you come up with the same Lewis structure. But if we look at this, we have an uneven distribution of charge here. We could draw one line of symmetry kind of down the middle here, and you might think, well, that's symmetrical, right? But it's actually not, because up here we have different stuff than we have down here, right? We have this hydrogen, these 2 hydrogen atoms down here, and then here we have a bunch of lone pairs. These are not the same. So if there's any way that you can look at this molecule and say that it's not even all the way around, then that makes it polar. So this is not even all the way around. We have different stuff on the top than we do on the bottom. If it's unbalanced at all, that makes it polar. So here we have these lone pairs, very negative up at the top here. We also have some polar bonds here. So these electrons are going to be pulled up here towards this oxygen because it's more electronegative. So that's going to make this a polar bond, a negative end and a positive end to this bond, a negative end and a positive end to this bond. So this is going to be a very positive end down here by the hydrogen, because we've taken all this negative charge and pulled it up towards the top here and made a very negative end up here. So this is going to be a negative end and a positive end to this molecule, making it very polar. So it's very important to know that water is polar, and we'll talk about some of the effects of that polarity in a few days from now. Alright, so if we take a look at these 3 molecules here, and we can kind of compare their polarity. So if we have CH4 and we draw the Lewis structure, we have C with 4 H's around it, and they're all going to be single bonded, and so we'll just end up with CH4 like so. So looking at this molecule, we could say that this is symmetrical all the way around, right? We have 4 H's all around this C, nice and even. There's no uneven or imbalance anywhere. It's all just even. So if it's even, that makes it symmetrical. That makes it nonpolar. Symmetrical, nonpolar. Remember, SNAP is how you can remember that. So we have a symmetrical molecule here. This is going to be then nonpolar. But what if we replace one of those hydrogens with a bromine? We'd then have carbon, hydrogen, 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 and bromine. And if we bond these all, we end up with a molecule that looks like this. So this is the same shape that we had before, but the difference here is now we've substituted in this bromine here. This is an uneven distribution of charge. We have the bromine over here, which has all these lone pairs on it. This is an uneven distribution of charge because we have a negative end here and then some hydrogens over here that are going to be fairly positive because the carbon is going to hold the electrons closer to itself. So this is going to be a polar molecule because it's asymmetrical. Asymmetrical is going to be polar because if there's any way that you can make this uneven, see, we could draw a line of symmetry kind of down the middle here and then this might look symmetrical that way, but the problem is we have an uneven distribution. We have different stuff over here than we do around here. So that's going to make it a polar molecule. If there's any way that you can see that it's uneven, that's going to make it polar. If we look at this last one, this is actually a tricky case because we have carbon, hydrogen, hydrogen, bromine, and bromine. So the problem with this is that when we draw these tetrahedral molecules on paper, a lot of times we draw them like this, and this looks like it's just this flat square. So you could kind of look at this and say, well, we could draw a line of symmetry down here, and it all kind of is even and symmetrical however we draw it. But the problem is that this is not actually the shape of this molecule. It's not a two-dimensional shape, it's a three-dimensional shape. So what this would actually look like is a carbon with a hydrogen on top, and then kind of a bromine coming off here maybe. And then if we draw like a perspective structure, we would have another bromine out here, and then another hydrogen down here. And so we kind of have these three elements on the bottom here forming kind of like the base of this pyramid type thing, and then the one hydrogen on top. So looking at this, this is actually not going to be symmetrical because we have kind of the bromines pointing away here and then the hydrogens pointing kind of towards us here, and this is going to make kind of a different end of this molecule on one side than we have on the other. So the other way that you could think of this, and I'll just erase this here real quick, is if we have, let's say, the same flat structure, but we draw it differently. So if we say maybe carbon with a hydrogen here, a bromine here, and a bromine here. This is actually the same exact structure as this. We haven't changed anything, but because again we're kind of representing this three-dimensional structure with a two-dimensional shape, it's going to look different like this. But here we can clearly see that there's no symmetry lines here. We can't draw a line of symmetry here. We'd be trying to match up this hydrogen and the bromine, and we also could not match up, let's say if we tried to draw a line of symmetry here, we'd be trying to match up this hydrogen and this bromine. So no matter how you slice it that way, this is asymmetrical. And if it's asymmetrical, that makes it polar. So again, any sort of uneven distribution, any sort of imbalance that you can see, that's going to make the molecule polar. Alright, so if we look at another example here, AlCl3, if you want to take a moment, pause the video, and draw your own Lewis structure here, but this is going to be Al with a Cl, and a Cl around it. We're going to have single bonds here, and then some lone pairs around the outside here, and this is where our Lewis structure would look like for AlCl3. So looking at this, we want to see, is it polar or non-polar? Well, we just want to see what is the symmetry. So looking at this, we have an even distribution all the way around, right? We have three chlorines, they're all evenly distributed. An even distribution means that it's symmetrical, which makes the molecule non-polar. Alright, so to figure out if a molecule is polar or not, the first thing you want to do is draw the Lewis structure out and see, is this molecule even all the way around? In this case it is. We have chlorines all the way around. It's therefore symmetrical, and then that would make it non-polar. Again, with SNAP, we know that if it's symmetrical, it's going to be non-polar. So another example here, oxygen. if we have oxygen bonded to another oxygen, you can again draw your own Lewis structure here, but this is going to be 2 lone pairs there, 2 lone pairs there, and then a double bond in the middle. This is going to be a symmetrical molecule because we can kind of form one line of symmetry down the middle here, fold the oxygens over, a line down here. Either way, it's symmetrical. So because this is symmetrical, that makes it again nonpolar. So this is even distribution. We have an oxygen here, an oxygen here. It's even all the way around. That's going to make it nonpolar. And that's it for symmetry. I hope this was helpful, and if you need to go back and look through any of these examples, feel free. Thank you.